Derivatives of trig functions is 3.5. We're going to talk about three basic things. We're going to obviously talk about the derivatives of trig functions. We're going to identify what each of those are. And we're also going to introduce simple harmonic motion, which is a periodic motion and uses the trig functions. And then we're going to introduce something called the jerk, which no does not mean a mean person. So we'll talk about that as well. So let's get started. The first derivative we want to come up with is the derivative of sine. You know that all the trig functions can be boiled down to sine and cosine. So if we find those derivatives, then we can easily find the other derivatives. So if we want to find the derivative of the sine of x with respect to x, remember the definition of a derivative is you take the limit as h goes to 0 of f at x plus h minus f of x over h. So if we fill this in, we're going to take the limit as h goes to 0 of the sine of x plus h minus the sine of x all over h. Now, if you don't remember your trig identities, you need to pull out that sheet from advanced math, or you need to see if you can find another one so that you have your trig identities, because we're going to use those a lot. So we use our addition identity here and write this out. And now we're going to simplify. We've got a sine x here and a sine x here, so we're going to pull that out as a common factor. Now we're going to start splitting this all up. So we'll have the limit as h goes to 0 of the sine of x times the limit as h goes to 0 of the cosine of h minus 1 over h plus the limit as h goes to 0 of the cosine of x times the limit as h goes to 0 of the sine of h over h. Now, these two here, you're going to need to look at your calculator. You're going to graph them and then set up your table as you get close to 0, or trace in really close to 0 and figure out what the limit is so that you can find that. This limit here is actually 0. Once you've graphed it, you'll see that. And this one is 1. So go ahead and pause it and actually look at that, because you need to know these are some of those limits that you need to know. This one we've already talked about, but this is another one you need to look at the graph. So here the limit as h goes to 0 of sine of x is just the sine of x, and then the limit as h goes to 0 of the cosine of x is just the cosine of x, because those are basically constants since we don't have an h in there. So when we put that all together, we get the cosine of x. So that means that we have the derivative of sine is cosine. Now, let's look at cosine. I'm going to use a similar technique. The limit as h goes to 0 of the function at x plus h minus the function at x all over h. And we're going to use, again, our sum rules. And again, it's going to split up very much the same way. So we pull out that common factor of the cosine of x. And then we split it up, as I say, almost exactly the same way as the other one. the limit as h goes to 0 of the cosine of x times the limit as h goes to 0 of the cosine of h minus 1 over h. And I am going to assume that you understand how to split this whole rational function up in this manner. If you don't remember how to do that, then you need to come talk to me so that we can make sure we've got that down, because that should be pretty solid. Alright, so we just talked about this when we looked at the graph, and it's 0. This one we've talked about several times, and it's 1. The limit as h goes to 0. Cosine x is just cosine, and then minus sine x, so we get negative sine x. So the derivative of cosine x is negative sine x. Alright, so now we've used our definition of derivatives to find the derivative of sine and cosine, and we can use that information and find all the rest of them. So we know that the derivative of sine is cosine, and the derivative of cosine is negative sine. So the other ones should be easy. Let's say we want to find the derivative of the cosecant. Well, that's the same thing as finding the derivative of 1 over the sine of x. So we can use our quotient rule here. Bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. And then we just simplify. So we have negative cosine x over sine squared x, which you can simplify to negative cotangent x cosecant x, because cosine over sine is cotangent, and then 1 over sine is cosecant. So the derivative of cosecant is negative cotangent x cosecant x. What about secant? Same thing. We're taking the derivative of 1 over cosine x. So we say bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. So if we simplify this out, we get sine x over cosine squared x, which is secant tangent. What about tangent? If you need to pause this and slow it down, figure it out, make sure you follow, make sure you do that. Bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Now, what is this? This is cosine squared plus sine squared, right? And from our trig identities, that's a Pythagorean identity, we know that's equal to 1. So the derivative of tangent is just secant squared x. And then last trig function, cotangent x. We're taking the derivative of cosine over sine. So we say bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. And here, if you notice, you have negative sine squared x minus cosine squared x. So you can factor out this negative, and again, that equals 1. So what we have is negative 1 over sine squared x, which is just negative cosecant squared x. So the derivative of cotangent is negative cosecant squared. These derivatives are something that need to be in your spiral index card study guide thing that you're making for the exam, because you will need to have these memorized. Especially sine and cosine, you can get away with not having the rest of them, but it won't make it any easier. It'll definitely be easier on you if you just memorize them all. Cosecant and secant, you just look at them and they go with their the same thing, and then the tangent one. So this is cosecant, it goes with cotangent.
All yearbook students need to come to the office right away, please.
And the negative goes with both the cosecant ones. The co ones have negatives. The tangent goes with secant, cotangent goes with cosecant, just like it does for its derivative. So any of those memory tricks you can use to get those, that would be great. All right, now why do we need these? Well, usually, often, a simple harmonic motion equation will have trig functions in them. And we talked about how position and velocity and acceleration were all related to each other. So we have position, and then velocity was the derivative of position, and acceleration was the derivative of the velocity, which means it's the second derivative of the position. And there's something else called a jerk, and that's the derivative of acceleration. It's a sudden change in acceleration. So it's the second derivative of velocity and the third derivative of the position. So this is the jerk. So we need to remember all what these that we learned and learn this new term here and use it for something called simple harmonic motion. And simple harmonic motion just means that it's motion where it's periodic. So like a spring bouncing back and forth, that's simple harmonic motion. So let's say we had a body that was moving in simple harmonic motion, and its position function was the sine of t plus the cosine of t. So this, remember, t is time, and then s is position. So the position of this body in motion is given by this function, sine t plus cosine t. Sine and cosine are periodic functions, so that means that this is a periodic function, and that means it's simple harmonic motion. Now, so what does that mean for the velocity? Well, the velocity then is the derivative. So the derivative of sine is cosine, and the derivative of cosine is negative sine. So we have our velocity function for this. Our acceleration is the derivative, take the derivative again, so we have negative sine t minus cosine t, because the derivative of negative sine would be negative cosine. And then the jerk would be the derivative of negative sine is negative cosine, and then the derivative of negative cosine is positive sine of t. Now, one thing that you'll notice here is if we took the derivative one more time, we'd be right back where we started. That's what happens with trig functions. You end up right back where you started because after a while, because they go back and forth. So if we had this body with simple harmonic motion, and we wanted to describe its motion, what was going on, well, we have all these different equations that tell us things about its position, velocity, acceleration, its jerk. And so how does that help us? Well, if we want to talk about its motion, for example, its position, then we would talk about where it started. So what's its position at 0? Well, the sine of 0 is 0, and the cosine of 0 is 1. This is one of those times you're going to have to know that unit circle. If you didn't get it last year, or if you need to brush up on it, make sure you do that. You will waste a lot of time if you do not know your unit circle. Then, so the position starts out at a position of 1 meter or foot, or whatever unit we happen to be using. Then we need to decide what its maximum is. Now, the way you find the maximum position is when the velocity equals 0. Now think about that. If we have a position function and it's going along like this, If we want to find this maximum here, what's the slope of the tangent line there? 0. Its tangent is velocity, so that's why we're using this velocity function to find when it equals 0. So we have the cosine of t minus the sine of t equals 0. Well, when does cosine equal sine? Again, gotta know that unit circle. So if you know your unit circle, you're going to realize that this happens at pi over 4, and then again at 5 pi over 4, and then around the circle every time. So what you write, the way you write that is that it's pi over 4 plus multiples of pi, where those multiples are integers. We say this k pi kes is how we've said it in our class before. So what this means is at time pi over 4, at time 5 pi over 4, at time 9 pi over 4, at time 13 pi over 4, and so on. Because it's periodic. It happens over and over, just like we talked about in the unit circle. You could just keep going round and round and round, and you're going to get the same answers with bigger angles. So what you need to do now that you know this time is figure out what your position is at that time. So our position will start with pi over 4. Our position at pi over 4 is the square root of 2 over 2 plus the square root of 2 over 2. Again, gotta know that unit circle. And then the next one would be 5 pi over 4, because that's when k is 1. 5 pi over 4, they're both negative. And then if you go back around to 9 pi over 4, you're going to be back here. And then 13 pi over 4, you're back here. So what does that tell you? Well, it tells you that we start here, and then we oscillate between these two positions. So we're oscillating between the square root of 2 and negative square root of 2. So if we have a number line, say, so here's 1 and negative 1. So that means that the square root of 2 is about here, and negative square root of 2 is about here. So if we started here, then we would go here, and then back to here, and then back to here, and back to here, and back and forth. We're going back and forth. It's a periodic function. It repeats. So that's what happens with the position. Now you can also discuss the velocity. When's the maximum velocity? Well, again, that's when the acceleration is equal to 0, because what did we say? When you have a maximum, this tangent line is horizontal, which means the slope of the tangent is 0, which means you use that derivative equal to 0 to find its maximum and minimums. So you can look at the velocity the same way, figure out when what its velocity is when its maximum velocity happens, its maximum acceleration, its maximum jerk, all those kind of things by looking at the derivatives. You just have to kind of think it through and make sure you're paying attention to how the function relates to its derivative. And sometimes that means a derivative with a second derivative, and so on. So read through section 3.5 and make sure you've written down any questions you have so that we can go over them in class.